Hi, everyone. I'm here in the building on Friday. That's our snow day. And I came in to make a couple of videos because I cannot be in class with you on Monday, which is our rescheduled class day because of the snow day. Turns out I'm on the committee for selecting the new principal, and I have to be there on Monday because that's when all of the interviews are taking place. So I've got to be out of the classroom. That's supposed to be a long day. From what I hear. So anyway, I wanted to do a couple of things. One is to go through a matched pairs problem from start to finish with you. I was asked about question 53 because a couple of students had issues kind of determining why we're in or recognizing why we're in a matched pairs setting instead of a two-sample setting, a difference of means. We're in a mean difference problem, not a difference of means problem. And we should drill down on why that is and how to recognize that setting. And then I want to take it all the way, from start to finish, make sure that we're okay on subscripting and make sure we're okay on checking conditions, which is a big thing. And then the last thing is make sure that that going from step 3 to step 4, going from the calculation of a test statistic and the associated p-value on into our conclusions, that we've got that buttoned up in a matched pair setting. And then I think after that I'm going to go into a two-sample problem, one involving, I'll see which one I choose. I haven't quite figured it out yet, but I did want to give you a good example of that because we're getting shortchanged on class time and we can't afford to slow down really. So, okay, so I hope you can bear with me while we go through this. The problem I'm looking at is it's on page, it's right here. It's number 53. It's the drive-through or go inside problem. It's on page 739. And what I've done is I copied down the data onto my page. And the first thing I want to stop and pause about is look down here at the language of the problem. I'm going to scroll in as far as I can, see if this will work. And do you see where it says, well, I grew up never being allowed to write in a textbook, so I probably shouldn't write in this, so I'll use a pencil. But there's some language in here that helps us spot this as a one-sample t-test for matched pairs. And that's this right here where it says the true mean difference. True mean difference is a mu diff, mean difference mu diff. That is not a difference of means. And I hate to sound all pedantic when I say that, but this is very loaded language. If ever you come across a problem where it uses the phrase mean difference, that is almost certainly a matched pairs problem, or matched data, or paired data, as it's sometimes called. Okay, so what I did is I read the problem, and this is where the two students, Patrick and William, use a random number generator to go visit, to figure who's going inside, who's going outside. But they're going through Dunkin' Donuts, and they want to compare the time for ordering the very same thing. Everybody orders an iced coffee. I guess every one of these orders is an iced coffee. And you get the time it takes to have that order filled when you go inside, and the same time when it goes when you go through the drive-through to get that same order filled. Now, another clue that this is a matched pair setting and not a two-sample setting has to do with the condition for two-sample problems, whether it's a proportions problem or a means problem. We know that one of the conditions is to have two independent random samples. That's not what we have here. Two independent random samples for a two-sample test. That's not what we have here. These are most definitely not independent of each other. These are all performed at the very same time, and the randomized quantity was who goes inside, who goes outside. So there was some randomization in here, but they weren't two distinct random samples. In other words, it would make no sense to create two X bars, X bar for inside and X bar for outside, and then investigate whether there is a meaningful difference of those two X bars. Instead, what we're going to do is look at the differences between these two things that were done simultaneously. That's another clue that they weren't independent. If every reading was taken simultaneously, that would be regarded kind of as an independence violation. There's one other thing to think about, and it goes back to when we were doing linear regression. Isn't it true that these are ordered pairs? You know, inside, comma, drive-through. You can almost plot these on a scatter plot, and you would see that every time you have one, you have another. It's almost like you have X's and you have Y's. And that's one way to conceive of this thing. Every ordered pair is what we're kind of considering. Okay, well, I created these deltas by going left to right. Now, I thought about this. Does it make sense to do that? And let me look at the problem. It says, many people think it's faster to order at the drive-through than to order inside. Okay, so if it's faster for the drive-through, the hypothesis, the alternate really, is that these times on average are less than these times here. So it makes sense to go inside minus drive-through. I wrote in minus out, and inside minus outside. And in so doing, what I found was when I did the subtraction, this minus that, this minus that, this minus that, I found that in fact most of the numbers were positive. Okay, so a positive value here means that the inside times were longer than the drive-through times. Okay, so that's consistent with what our hypothesis is. Furthermore, my opinion is that it's easier to analyze positive numbers than negative numbers. Your head spins a little bit less when you're trying to make sense of the data. Okay, so now I have this stack of numbers here, and I put a box around it because this is now the data on which I'm going to perform not only the test, but I'm also going to be checking conditions with that data right there. Okay, so I think it's time to start the party. Let's do one last thing, just so it goes a little faster when I'm working through the problem. I'm going to install these numbers into a list. Could I have done both of these numbers? I could have installed this in list 1, this in list 2, and then let list 3 equal L1 minus L2. That would have been perfectly fine. I was just feeling, I don't know, lazy or something. So here's my calculator. I'm just going to install these numbers in the box. 7, 13, 4, negative 5, 11, 1, 2, 6, 3, and negative 3. And I should have 10 numbers. Is that right? Yeah, 10 numbers. Okay, I'm going to set that aside for the time being. And let's start the procedure. Okay, so step 1 is to talk about the population and the parameter in question. Okay, so the population, let's use context here. So the population would be, I don't know, consumers of Dunkin' Donuts. I read somewhere recently that they changed their name. They're no longer officially called Dunkin' Donuts. Now they're officially just called Dunkin'. It's an old Boston company. Okay, we'll see if that holds up, and if I need to edit that, I can come back and do that. Okay, the parameter is going to be mu diff, the mean difference in order, what do we call these, order times? I think order times. Inside minus outside when ordering iced coffee. Now, that's interesting because it's possible that when they order something else, the data doesn't hold up. It's because it could have to do something with, I don't know, the interior layout of the store. Maybe the coffee stuff is sitting there right by the window, but maybe if they ordered, a dozen donuts, they have to go to the front. They have to go to the front desk, and maybe this data wouldn't hold up if you change the game. So I'm being a little bit precise there, but I did lead off with my symbolic representation of my parameter. It is a mu diff, the mean difference. And that's a nice translation, Greek, mean, mu. But now we need hypotheses. So the null hypothesis is that on average there is no difference. In other words, the mean difference equals 0. On average, there is no difference. And the alternate, and let's get this right, because I subtracted inside minus outside, that means that I'm on the lookout for a positive mu diff. So that mu diff is greater than 0. So let's capture this in words so that we're ready to do some writing when we get to step 4. So this would be, on average, there is no difference in times. I'll leave it at that. I know that I could write more, but I'll leave it at that because we've already discussed that up here a little bit. Now, the alternate is that on average, inside times, I wrote indide. That's not very good. Inside times are longer. Okay, and again, that's not a complete, I could write more to be better about that, but I've already defined the parameter up here, so I think there's no lack of understanding at this point. Okay, I think I'm okay with my population parameter and my hypotheses. It's good to stop here and make sure, especially that you have that symbol going the right way. That on average, this number that we calculate is greater than 0, positive. Okay, step 2. Oh, and by the way, please, again, don't ever write, for instance, x bar diff equals 0 and x bar diff greater than 0, because those are statistics, not parameters, and we don't mention statistics, the values coming from our sample, in our setup of the problem. Okay, that's only what we are hoping to learn about by using our statistics instead of our parameters. Okay, step 2. Our conditions. We have a randomness condition. Oh, wait, let's talk about procedure. I always forget that. Our procedure is going to be a one-sample t-test for matched pairs. For matched pairs. Okay? Or you could say a paired one-sample t-test. That would also be good. Matched pair, the only reason I would hesitate is that when the matched pairs is really the language of an experiment, which isn't bad. Was this an experiment? Did we apply a treatment when we did this problem? I kind of think we did. The students went in there and they applied the treatment of location. They decided which place to go to order their coffee. So that's fine. Okay, now the randomness condition. What is randomized here? Well, we randomized the order in which the coffee was, the orders were placed, or who ordered what from which location. There is some randomness there. We also maybe could make an assumption. We must assume that these 10 visits could be considered a random sample drawn from all possible visits to Dunkin' Donuts, to DD. Okay, so that's kind of an interesting condition in this case. I think the way we did it is pretty good. We have to assume this was, we have to assume these 10 visits could be considered random. Okay. Furthermore, he's trying to extend, when you think about scope of inference, these two students are trying to make a grand claim about, drive-throughs. I guess not so bad, for this Dunkin' Donuts. So I guess maybe I'm going too broad to this Dunkin' Donuts. Maybe that's better, okay? Just so we don't exceed our possible scope of inference. Okay, now what else do we have? We have a 10% condition. Well, there are certainly possible to do more than, 10, to develop more than 10 of such paired observations. So it is possible. These 10 pairings are certainly fewer than 10% of all possible such paired visits. And I like to slip in a little bit of context when I'm writing my conditions, because the graders are always looking for context everywhere you look. And if you have to make claims like this, it's good to butter them up a little bit with context. Okay, what else do we have? We have a condition that has to do with normality. I'm going to turn the page here. And I'll save these pages if anyone wants to take a peek at them. Okay, so we're still in step 2. Step 2, continued. Okay, now this is the normality condition. Well, let's go down the list. Do we have evidence of a normal population? Now, this is crazy. Believe it or not, this is a sample drawn from the population of all possible such pairings of visits. If you did, a different set of 10 visits simultaneously, one person goes inside, one person goes outside, I could keep adding to these numbers forever. So this is a strange population. It's out there, and it doesn't exist yet until, unless you were to do this for the rest of your life, go in, have a friend and keep visiting Dunkin' Donuts for iced coffee. It's not like that population already exists. So in any case, we don't have a claim that the population is normal, nor do we have a large sample size. This is only 10 in our sample, so n equals 10, which means we have to look at the data in our calculator. Okay, so let's see what the calculator drags in. I'm thinking, what would be the best way to get at this? So I'm going to do a couple of things. First thing I'm going to do is look at a modified box plot, second stat plot. And let's go down here. And I want to look for skew and outliers. That's kind of the usual. Those are the usual culprits when we have a normality violation. I think I'm all set up good. So I go zoom stat. And I see that, and you could hardly ask for nicer data, huh? If I hit trace, I can see, 13, there's 7, there's 3.5 for my median, first quartile 1, and minimum is -5. So this is almost too good to be true. But I'm going to copy that down, and this is in my procedure. That median is slightly off center, but you could really hardly ask for a better looking box plot. So let's put some language around this. A modified box plot. I want to say not just of the data. We should get out of that habit and don't just toss the word data around all the time. Let's call it modified box plot of the differences. Reveals no evidence. I'll say no strong evidence of skew or outliers. T procedures should be safe. Again, this is almost too good to be true. You don't need to label that really. I think it's good enough just to have a sketch. It doesn't have to be brain surgery. Now I want to show you another plot that we might also put up here. If I went second stat plot on, and we look at the normal probability plot, okay, the NPP. So I've chosen that, and I go zoom 9, and I look at this, and remember that in an NPP, a straight line is indicative of normality. In a perfectly normal setting, these dots would be exactly along the line. This is not bad. Again, you almost couldn't ask for better. I'm going to put a sketch of that also. So I'm just, sketching this, 1, 2, 3, 4, 5, 6, and then there's a little jog like that. And we can say something there about this too. And NPP shows a linear pattern which is suggestive of normality within the sample. And so that gives credence to a claim that it arguably was drawn from a normal population. Okay? So I think this is enough. We've addressed it two different ways, and we've made a conclusion about T procedures should be safe. So I think that's going to be good to go there. Okay, on to step 3. Now this is something I noticed when I looked at the homework today. I'm seeing some students who are devolving into what I'd consider to be sort of sloppy step 3 stuff. But while before we start in on the numbers, let's see what the calculator gives us for the sample numbers. So what can we do? Maybe if I run the test first, it'll tell me all the key numbers that I can use to create my test statistic. Stat test. We are doing a t-test, just a one-sample t-test. It's the very first option there. And we, for once, have data. We don't just have summary statistics. We have the data. Our mu naught is equal to 0, and our null is, in fact, greater than 0, right? If I go back to my step 1, we have mu diff is greater than 0, greater than mu naught, which is 0. Okay, so let's look at what we get here. Come down here, everything looks good to me. And this is a one-tailed test, not a two-tailed. Okay, so hit calculate. I'm going to write down these numbers because it's almost as if whoever designed the calculator knew that you're taking AP statistics. Okay, I'm going to write these numbers down. I see X bar diff, don't forget the subscript, is equal to 3.9, and I see S, that's the sample standard deviation, is equal to 5.646. Now, I'm just going to keep my calculator handy while I do the work. T is equal to, let's see, X bar diff minus mu diff naught divided by S diff over the square root of n. And I can write that down to here. N equals 10. N equals 10. It does not equal 20. I don't know why I have a... No, there's my mouse. Got it off the screen. Okay. Now, this equals 3.9 minus 0 over 5.646 over the square root of 10, which in turn equals our t-score, which is given to us right there, 2.184. 2.184. Okay, now this looks really buttoned up, and I know that sometimes when you have two sample stuff going on or pooling going on or any of those funny other things, this can be a drag. But this is error-free. This shows what we're doing. This shows the substitutions. It shows the test statistic. Please don't forget to write t equals. That is a commonly left by the side of the people to start right in here. And again, it just downgrades your momentary reputation with the grader. Now, how are we going to package the p-value? The probability that t is greater than 2.184 is equal to, looking at my screen, 0.028, and I think, how about 0.0284? I'm going to put a little dot to indicate that's an approximate value. Now, we were told in the problem to use alpha 0.05 as the, hold on here. There's a little problem, and I want to show it to you because I may have fallen into a trap, but I also think that the question could have been written a little more clearly. This says, do these data provide evidence of a difference? That's a two-tailed idea. even though up in here it said that many people think it's faster to go through the drive-through. So I think I fell into a trap. I crafted my hypotheses as if I was reading up here, which disagrees a little bit with the way they present the problem formally down here. So I'm going to go back to my hypotheses, fix the hypothesis, and then show you what I do with the p-value. Okay, so I'm going to go back to here and say this becomes not greater than, but not equal to. Okay, on average, there is a difference in order times, inside or outside, inside or drive-through. Okay, so that was on average there is a difference. I am glad I caught that, and I think that's a little bit of a teaser, not a teaser, but I think that's a little bit of a flaw in the way the question was presented. But that's our job, is to catch that stuff. Okay, so now that is a one-tailed p-value. So I'm going to say p-value, not just probability, is equal to 2 times 0.0284, which equals, what's that, 0.0, I better use the calculator to do that. But let me show you what I'm going to do. I'm not just going to multiply those two numbers. I'm going to go back and run the test again. So stat test, t-test. I'm going to come down here and change my alternate hypothesis line to that one, not equal to, calculate, and there's my new p-value, equals 0.0568, okay? All right, so that's what that happens when you double that, and you get the very same thing. All right, now, what do we do with that number? I guess we've got to compare that to 0.05 using the word because. Because 0.0568 is greater than alpha of 0.05, we're going to fail to reject H naught and conclude. So this is all, we're sort of finishing step, I'll call this all step 4, that's probably smart. Because this is greater than 0.5, fail to reject and include that, now we have to be careful here, evidence from this sample of visits to Dunkin' Donuts does not show significant evidence of a difference in order times between inside and drive-through ordering. Now, this is an interesting problem, because if we had gone with a one-sided alternative, we would have found significance, right? If we had just posed the problem a little bit differently, that hypothesis that it's faster to go through the drive-through would have been supported, but we can't say that because of the way the question was posed. That's kind of awkward. It's like, oh, really? But now let's go through this and make sure that we've done all the right things. Did we link our p-value to our decision about the null hypothesis? Yes, we did that right here. Did we then draw a conclusion about the alternate hypothesis? Yes, we did. The alternate hypothesis was evidence of a difference. There is a difference. Okay, when we go back to here, remember the mu diff not equaling 0 means there is some non-zero difference. Okay? So that was good. And the last thing to check is, did we do this? Did we answer the question that was asked? Do these data, I'm reading from the book now, do these data provide convincing evidence of a true mean difference in service time inside and at the drive-thru for this Dunkin' Donuts? Okay, how do I do? Does not show, and then this is significant evidence of a difference, of a mean difference. Let's make that improvement. Of a mean difference. That was a critical shortcoming in my writing. Okay, that is very important to have said that. In order times between inside and drive-through ordering. Okay, going to leave it at that.